Okay, good.
Okay, awesome. Thanks everyone for joining. So yeah, we started the session and should be good to go. Tomorrow's, yesterday's session is on YouTube. I pasted the link here. I think it's also on the chat, but I'll go ahead and paste it again for people who joined late. And today's session will also be in the same playlist.
Yeah, thanks everybody for joining. I know this is towards,
Sorry about that.
we've heard enough of that guy.
So yeah, today we'll be, we saw this diagram yesterday, and today we'll be looking at the deep learning aspect of it. We saw that deep learning is a subfield inside the machine learning, and we'll go in detail in what that is. Before I go to the other slides, I just want to give a brief history on when deep learning came along. You might be actually surprised that it came in 1940s and 50s, so the concept was already built then. But during that time we didn't had enough computational resources, this integrated knowledge base, so it didn't really pick up until recently. But the big breakthrough for this deep learning came along during the 1980s, when the back propagation was introduced. So we'll see in detail what back propagation is and how that plays a vital role when you're training a deep learning models. Amil?
Yeah, actually, I just wanted to add something. So I guess we didn't, yesterday we kind of took that poll of, where people stand with regard to their expertise in remote sensing, et cetera. I'm sure that, some of the people on the call have used the software Envy. And I do recall that, from, over 10 years ago, Envy had what they just called a neural network classification, supervised classification function in their software. And so that was, I guess, an earlier form of deep learning already integrated into the software. And then I recently looked up and I see that now Envy has, modified that to, I guess, the current version of Envy has TensorFlow as something that they're running. And then for those who are also familiar with Idrisi or Turset, they also have, neural network functions in Turset for, running these things as well. So just an interesting, tidbit in case there are people who, have used Envy or Turset, Idrisi, et cetera. Thanks, Biplav. Back to you.
Thanks, Amil. That was a nice addition to that. I didn't know that. Thanks for the information. Yeah, so the deep learning actually began taking this kind of shape in 2006 and 7, but it really started hitting in 2010s when AlexNet, which is a form of a deep neural net, so there is a challenge called as the where computer scientists, computer vision experts come in and apply different kind of algorithms in what is called the ImageNet dataset. So in after 2012, the AlexNet won the ImageNet competition, and it actually increased the accuracy by more than 10%. And that was when the deep learning, the era of deep learning, really emerged. And after that, literally every week new algorithms come up, and it just it's a it's a great time to be in this deep learning era. So just a background on that. Yeah, so we already know that deep learning is a particular kind of machine learning that does some form of abstractions in the real world concept, and then train those abstractions to learn a different kind of representation of the input data set to produce even output. Here I have linked this really good book by Ian Goodfellow. It's the deep learning book, and it's open, and it's one of the One of the really good book that I like to suggest to everyone. It goes from the introduction, but then it also builds on some of the mathematical foundation on how these deep learning actually work under the hood, and how you can use in your workflow. So I highly recommend checking this book out. Oops. Okay. Sorry, here's some problem with sharing. Awesome. So can you all see my screen?
Yes, we
Yep.
can.
Okay. Yeah, we saw this diagram yesterday also. We talked about supervised learning, unsupervised learning. We'll also look into that a bit detail in the later slides. But in today's session, we'll be focusing on the deep learning aspect of the supervised learning. There are, again, different kind of deep learning architectures that you can use depending on what kind of problem that you're trying to solve. And it's just two representative frequently used algorithm on the CNNs and the RNNs. Uh, so it really boils down to what kind of research question or what kind of problem you have in hand. And almost all of the deep learning algorithms can be broadly classified into these four categories. Um, Supervised, unsupervised, semi-supervised is somewhere in between supervised and unsupervised, and reinforcement learning. So a supervised learning, I'm pretty sure you're all already aware of this. Supervised learning involves, training a model on a label data set. That means each of your input point has a corresponding output label that it tries to learn the patterns from those label data set. So the ultimate purpose is to predict or classify unknown data points based on the pattern that the model has already seen from your label dataset. Some of the examples of the supervised learning are the regression tasks. For example, trying to predict the price of a house based on different kind of features like its size, location, number of bedrooms, etc. It could also be a classification tax, land cover classification we all are familiar with. Something outside of that could be, classifying an incoming email as a spam or non-spam. And this is sort of the algorithm that Google applies under the hood to classify your emails. Uh, yeah, and then there are different kind of methods that you can apply under the supervised learning. Linear regression, logistic regression, support vector machine. We talked a lot about random forest yesterday. Neural nets is another method, so we'll be focusing on neural nets today. uh, the pros of this supervised learning is that it can give you very high accuracy, because you have a label data set for the model to fall back on and learn those patterns from. But the downside of that is that it needs those label data, which means it could be very expensive or time consuming in order to train or obtain those data sets. And there are several, again, I said that these architecture come out like every week, and there are like several others that I haven't listed here, but these are some of the famous that often used in the literature and in several kind of problem. Deep neural net, DNN, is the one that we'll be looking on today. And there are recurrent neural nets, which is when you have a time series of data set, you could apply these recurrent neural nets. There is CNN, which applies a convolutional on the images. So there are like tons and tons of algorithms out there. But some of the concept that will go in this lecture would be helpful in understanding almost all of these neural nets. Okay, Okay, so the next type is the unsupervised learning. Basically, the unsupervised learning is where you don't have any pre-existing labels. So you're not telling a model the answer, what to look for. Instead, the model looks at the data itself and then try to infer some pattern or structures from the data. So unsupervised is often used for clustering algorithm. We talked about that yesterday, k-means clustering. They're often also used in dimensionality reduction. So principal component analysis is one of the unsupervised learning that often used in the remote sensing world. Some of the methods, as I mentioned, k-means clustering, principal component analysis, autoencoders, etc. So the pros of the unsupervised learning is that it doesn't require any label data. You can just throw in whatever data you have, and it will try to come up with some sort of patterns or structure from the data itself. The downside of that is because you don't have any ground truth to compare it against. Uh, it's very hard to evaluate the performance unless you know what you're doing or you're very familiar with this area. So here on the right, I'm showing you an example. This is a district called Paro in Bhutan, and it's a major rice growing district in the area. And on the left side, you see the classification provided by the RLCMS, the Regional Land Cover Monitoring System of the Hindu Kush Himalaya. It has several different classes in it, but this particular area only have 3 or 4 classes associated with it. And then on the right side, I ran a k-means cluster on the this is on the planet data set. So this is on roughly 5-meter resolution. And because I know what different different pixels represent, or what are the classes that are in that particular area, I ran it through a k-means cluster, and it gives me very similar results. So depending on your use case, k-means clusters or any kind of unsupervised learning could be really beneficial. The other type of learning is this called as the reinforcement learning, and this is not something that we usually use in remote sensing world, but it's very cool, and just wanted to put that out. So the reinforcement learning, I'll give it by saying an example. So self-driving cars or autonomous vehicle are an example of reinforcement learning, where you have some sort of a problem in hand, and then you have an agent. So the agent in this case is autonomous vehicle or self-driving car itself. Based on the agent is then provided some sort of the environment to learn from. So in case of the self-driving car, that would be a driving environment that consists of the traffic signal, other vehicles on the road, your or the ramp, or all those driving environments that we often see are the environment that's provided to the agent. And then there is something called as a state for that particular agent. So in this case, the state for the agent would be, for example, the speed of the vehicle, the position of the car, the position of the other vehicle with respect to the car. Based on that state, it needs to do some sort of action. So action in this case would be like whether to accelerate or whether to deaccelerate, whether to turn left or right. All those are the actions. So once the agent on an environment does some form of an action, then it's provided with some form of a reward. And this reward could be a positive reward, or this could be a negative reward. So a positive reward would be when it's on its lane, it's driving safely, it's comfortable, efficient. But a negative reward would be like if there's a hard brake, or if it crosses the traffic light, there's a traffic violation. All those would be a negative reward. So it's a different way of thinking in this machine learning world, but it's something out there, and it's good to be aware of. Yeah, so now in this one we'll just focus on one particular type, that is the deep neural net, often called as the artificial neural net. In any kind of deep neural nets, you'll see there is three major layer. You have an input layer, you have a hidden layer in between your input layer and your output layer, and then based on the learnings on these hidden layers, you'll get an output layer, and I'll go in detail in each of them in the coming slides. But each of these what you're seeing here, it's called neurons, and each of these neuron represents some form of a learning, and there's some form of a mathematical computation that goes in each of these neurons. So I know many of us here are a mathematician or have a major leaning on that. So if you are looking, a mathematical definition, ANN is something where you map y with f based on some form of a parameter, and the value of these parameter theta, which is represented in this case, is learned based on the example data sets that you provide to those algorithm, and it will determine those parameters that will result in the best approximation of that function. Again, I'm taking this from Ian Goodfellow book, highly recommended out. So we talked a lot about random forest yesterday, and we saw that we ran an example and saw that it actually gives really good results. But as your number of data sets keeps on increasing, then some of these older algorithms might not be able to handle some of these data, and that's where you really want to use some of these modern algorithms to make use of this data volume that will only go on increasing. Here we have an example. We have an image of an airport. You can apply some form of an object detection method where it's detecting this airplane, and it's providing you with this bounding box of those airplane. But you could also move forward one step, and then instead of just getting the bounding box, you could also actually segment that particular object that you're interested in, commonly called as the instance segmentation. I know from yesterday's Menti, we saw some response on people saying that instant segmentation is something that comes into their mind when people talk about machine learning. So yeah, here it is. And then you could also take that a step further, and instead of just classifying or just segmenting a particular object that you're interested in, you can actually segment everything on that image. Kind of like an land cover maps that we see in our world. So yeah, I this is again linking back to why we might be interested in using these artificial neural nets. As I mentioned, that 2010s was when the deep learning really started to kick off, and this diagram is basically showing you that your number of neurons are increasing as you are applying these newer algorithms to learn your representation from. But that also means that your classification error is actually going down. So this is an example from this ILS-VRC. So this is again the ImageNet dataset. Let me quickly share that over here. So this is the data set that we're talking about. This is an ImageNet large-scale visual recognition challenge. This has around 1,000 classes within that data set, and they have like millions of training data, thousands of testing and validation data set. And every year there's this ImageNet challenge where people and researchers from all around the world come in and compete in this by providing newer set of algorithms, newer set of ideas. And So this is basically saying that in 2012 when the AlexNet came in, and if you look at previous algorithm which were not based in deep learning, your error rate actually started to go down significantly. So this was sort of the break point in the DNN world where everyone was jaw dropping. Your error will decrease by more than 15%. And ever since, newer algorithms have come up and these error rates have gone down. Okay, so there was sort of a little bit of background on why we might be interested in using some of these newer algorithms out there. Uh, this is TensorFlow training, so it's good to start with what a tensor is. A tensor, you can think of it as a generalized form of a matrix. Every tensor has a dimension called as the rank. So there is we know of scalar, which is sort of a zero-dimensional data sets. It just represents some form of number in it. And then there is something on 1D or the one-dimensional end, which we refer to as a vector. You could have a row vector or a column vector. And then if you move to one more dimension, you have a matrix. The matrix usually have a rows and columns and the value in it. The tensor is really the generalized representation of the matrix. So a tensor could be 3D, 4D, 5D, 6D, whatever tensor it is. It's just a generalized representation of this matrix. So when you say TensorFlow, it's actually moving this tensor from input hidden to output layer. So the name came from the movement of the tensor itself. Yeah, and moving on, I think we briefly talked about labels and features yesterday. And you'll often encounter, when you're talking with someone in the conference, they will talk, what are the number of features that you use? Maybe you can drop some of those features. So uh, a feature is usually a predictor variable. You can think of it as an X in case of a simple linear regression. If you have a very simple machine learning project, it could have a single feature. But if you have a more sophisticated machine learning project, you could have as many features as you want. And not all of the features might be helpful. So we'll also see like how you can choose what's the right features to use later on the slides. And then there is a label, also known as the response variable. So a label is something that we're trying to predict. Y variable, if you're thinking of a simple linear regression. So a label could be, in our case, we saw the median house value based on different features like age of the house, number of rooms that are available, number of bedrooms, all these features. And here on the left side, this is an screenshot from an iris flower dataset. So the features in this case are, the length and width of the sepal or the petal. And based on those features, you're trying to find what kind of flower is it. Okay, so now we have some basic understanding of different components. Let's go back and look at some of these input, hidden, and the output layer. So your input layer is where the network actually receives your input data set. There's a lot of operations that goes, pre-processing that goes in before your input layer is ready. But once the input layer goes into the network, it's then passed to this first hidden layer. And each of these, even the input layer has the neurons in it. So each neuron in these input layers represents some form of features, as we saw before. And then the hidden layer is where majority of the computation within the network take place. And this layer again comprises of many neurons which are connected with each of these neurons are connected with previous neurons. So if you look at this particular neuron labeled as 0, you see that it receives the input from sepal length, sepal width, petal length, and petal width. Since all of these neurons are interconnected with each other, that's why the name come as a deep neural nets, where it's just interconnected with each of these neurons and learning the representation from each of them. So here on this 0, there's once it receives the data from the previous input layer, there's some form of mathematical operation that goes in it. Once the operation complete, then that the output from this particular neuron is provided as an input to the corresponding hidden layers or output layers, in case if you only have one hidden layer. And again, taking this from Ian Goodfellow book, if you have, for example, a picture, you put that as an input layer. You could have an RGB layer, or you could have as many layers as you want. After the input layer, the hidden layer learns different representation of those input layer. So your first hidden layer might be learning edges of the input layer, or your second input hidden layer might be learning all these corners and contours that are associated with that input data. And your third hidden layer might be learning object parts like head, or if you're trying to classify your car, then it might be looking at those wheels and whatnot. And then based on these learnings from the hidden layer, the output layer is where you actually try to predict. That's more useful for us, like it will tell you whether it's a car, person, or an animal in this case. The last layer here is the output layer. So the output layer is where the final output of the network is produced. We're looking at the iris flower data set here, and in this case, the output layer is a probability. So if you sum these, it's equals to 1. So it's providing a probability that that particular input belongs to a certain class. So in this case, based on the input layer, it's the network is telling us that it's very high. It's very likely that particular input layer is a very versicolor flower. So when you put all this together, you have some form of a label, photos, cats and dogs in this case, and then that goes through some form of these hidden layers where the neurons inside the hidden layers are learning several form of representation of those input data sets, and then that provides you an output. Okay, so now we have some basic understanding on different layers that are involved. Let's go and look at some of the core concept on how these neurons are actually processed or implemented. So a neural net is also referred to as feed forward net, and it comes from this forward propagation that it does. So what it's trying to do is it's processing, or it's passing the input data through the networks layer by layer, from your input layer to a hidden layer to your output layer. And during this passing, or during when the data is put forward into the network, each neuron on the network performs some form of a mathematical operation on its input, which then produce an output, which is input to the subsequent layers that would come in. So if we look and zoom down to a particular neuron, let's say we look at this particular neuron. This particular neuron receives input x1, x2, and x3. And it also has some form of a weight associated with it, which is W1, W3 for x2, and then W5 for x3. So your H, which is an input, your H1 input would be the matrix multiplication of your input data set x1 multiplied by your weights. So h1 in is w1 times x1, w3 times x2, and w5 times x3. And then there's some form of a bias. If you're looking at a simple linear regression, you have like y equals to mx plus c, where m is your slope and c is some form of a bias or an x-intercept. You can think of the bias in a similar way. So there's form of a bias that's added to those weight. So the input to this particular neuron, we have it. But once we have those input, then there is something called as this activation functions, and we'll look into detail what those are. There's some form of a mathematical functions that are applied on those input that will give you the output. That's I out in this case. So the data have flown from x1, x2, x3 to this particular neuron that I'm showing here. The output of this neuron is now the input of this particular neuron, which is the last neuron here in this case, the green one. So the weighted sum again, u1 is again the weight similar to w1. It's just representing a different value here. U1 times the output from h1 times u2 plus u2 times the output from the h2 is then provided as an input to this particular neuron h3. This is where again the activation functions would come into play and would give you the final output here. So we have like one layer of data that goes from input hidden to the output layers. But we know that it's not going to learn in one go, right? So there's some form of an error associated with it. And we know that because this is a supervised learning, we have a actual level data set associated with it. So then the network will compute the error by comparing its output with the desired output. And that's usually done using a loss function. And we'll look at what those loss functions could be. So this is sort of a basic concept on how the data are flowing across these different form of layers through thousands of these neurons. So once your error is now determined, then you'll need to go and distribute that error so it can adjust those weight. So this is what the back propagation is doing. So a back propagation, sometimes referred to as back prop in short, is the process where you try to adjust the weight of this neuron based on the error that it's producing from its output. So a common form on how it's usually done is it will compute a gradient loss. So it will look at the network's output, it will look at the desired output, and then it could compute a form of a gradient. And it compute that gradient using the chain rule of differentiation. So, linear algebra, all those things that we learn would come into place here. Once those gradient are determined, then those errors are then back propagated, starting from the output layer to the last hidden layer previous to that, and then finally to the input layer by making an adjustment on the weights of each of these neurons so that it could reduce those error at the end. So as I mentioned before, the back prop came in like 1980s, and this really changed the way that people train this model. And believe it or not, backprop is still the similar concept that we apply in majority of these modern machine learning algorithms. Okay, so now we know how data is moving forward, how it's adjusting its weight, but there were some, activation function, loss functions that were applied in between. So the activation functions are usually a mathematical function that introduce some form of a nonlinearity in your neural nets. If you have linear data, you're better off not using machine learning algorithms. You could just use simple linear regression. But if there's some form of a non-linearity, you could capture that using the activation function. So these activation functions are applied element-wise on every neuron in the network, and this actually helps to model this complex relationship on this data set. So some of the commonly used activation functions are sigmoid functions. So a sigmoid function, you'd use a sigmoid function normally in a binary classification because it gives you an output between 0 and 1, and you could interpret that as a probability associated with your output class. Or you could have a simple ReLU function where you're just trying to preserve a positive values in your neural nets. So if it encounters anything less than 0, it will assign that to a 0, and if it encounters anything greater than 0, it will assign it to whatever value that is. And here's actually a notebook that that basically goes and just using a numpy and producing the data set, it shows you how different kind of activation function could look like. So I'll will suggest also, if you are really interested in diving deep, go and check this notebook out. The next important concept is the loss function. So the loss functions, we saw that once the output from a forward propagation is produced from the network, then it computes the error associated, normally using a loss function. So loss function is again a mathematical function that helps you to quantify the error associated with your network and the actual value of the actual level value. So it helps you to converge your training by finding an optimal value that would minimize those loss. Some of the commonly used loss functions, again, it depends on what kind of problem you're trying to solve. But if you're trying to solve a regression based problem, an example would be trying to predict again the price of the house. It's a regression kind of problem, so you could use a mean square error loss. A mean square error loss would um, put in more error, because it's a square of your error function. So if you have a larger error, it would penalize more on that on those values. You could even use a absolute error function, or you could use a Hoover loss function, which is somewhere in between a mean square error and a mean absolute error. If you are doing a binary classification problem, which we'll go into today, you could use a binary cross entropy function or a Hinge loss function. If you are doing a multi-class classification, you could use multi-class cross entropy, KL divergence loss, all these functions that you could use. Okay, so the next important concept is of the optimizers. The optimizer is so once you know what's your error or what's your difference associated with it, then you need to because you calculate a gradient based on your input, based on your desired output and the output from the network. You need to move that in an opposite direction of the gradient, and optimizers come into play in that aspect, by where they will when the network is back propagating, they will iteratively update your parameters based on those minimized loss. One of the major or significantly used algorithm is something of a gradient descent. So gradient descent, you can think of it as like going downhill. So when you are trying to move from, let's say, the top of the hill to the bottom, there are like different paths or different ways that you can go there. You can take this green one or purple one, or if it permits, you could even take this direct one. So optimizers help us navigate that path when it's moving downhill. You can sort of conceptualize it in that way. And there are various variant of the gradient descent. A batch gradient descent is where you give all your data to the network at once, and it will compute those gradient loss on all the data that you have. So a batch gradient descent might be really useful if you have, like, let's say, smaller set of data. But if you have like a large set of data, which in case of machine learning they usually have, um, it's not a good idea to give it all at once, because you don't have computational power to calculate it, and b, the training is very, very, very slow. So this is where the stochastic gradient descent comes in. The stochastic gradient descent is where you just give one example at a time to the network. So it will learn on one example, it will move it through the network, it will calculate the error, it will backpropagate, and then adjust those parameters. Uh, you could also do that. That's something called as the stochastic gradient descent. But again, that might not be a good idea, because then you are looking at individual data sets, and you're trying to adjust your parameters or your weight of the network based on those individual example, and you might actually be overfitting on your data set. So when you try to predict on a new data set that the network has not seen, it will just blow out, because it hasn't seen those patterns before. And this is where this mini batch gradient descent comes in. So it's somewhere in between a batch gradient descent and a stochastic gradient descent, where you take a batch of a data, you pass it through the network, you calculate the loss, back propagate it again through the network. And this also helps us get rid of, if you have millions and billions of data points, because you're only training on some specific batch. You can run that, so you don't have to worry about those kind of things. Okay, so now once it calculates those gradient loss, when it's calculate those loss, it needs to move in the direction. So for example, in this case, when you're moving from top of the hill to the down, there's an important thing that you need to take into consideration, and that's the step that you want to go down. You don't want to go like jump, because then it's a very, very likely that you're gonna die. But you also don't want to take it too small, because there are other conditions that might be associated with it. So this is where a learning rate comes into play. So this is an hyperparameter. uh, Hyperparameter is something that you specify to the network yourself, and it basically controls the steps that should be taken by these optimizers when they are optimizing your or when they are updating your parameters value. So you don't want to have it too large, because then you'll always overshoot, and you'll never reach to that global minima point that you're trying to go. uh, you don't want also to have it too low, then you're taking very small steps, and it will take a very long time to train the model. The other downside is that there could be a global minima, and then there could be a local minima. If you're taking a too low of a learning rate, your algorithm might be stuck in a local minima and never be able to out of it. So you need to take those steps just right. And because it's a hyperparameter, you basically have to play and see how it performs. I think this is the last one on some of the terminology I have. So the next one is the dropout layer. The dropout layer, as the name refers, is basically you're randomly dropping some sort of the neurons while you are training your model. And you want to do this because if you have very large data set, and if you have like tons of neurons, then your network might be overfitting and actually learning on some of the nuances that it's not necessary, or it's not like really important. So with dropout, you could avoid some of these overfitting that could go on. or if there is a sequential dependencies of the neuron. So for example, if the output is determined based on what the previous neuron has see, you also don't want to have those kind of sequential dependencies, because your new data set may not have those. So dropout can help you in, basically overfitting your data set, and sometimes it's also necessary to lower your cost of computations. Okay, so those were like some of the major terminologies, concepts that would help you go and tackle any kind of neural nets kind of problem. And here I have this example from actually from the TensorFlow team, where you can run some of these neural nets on your browser. So let's go and look at these. Okay, so now here, what we have here is we have a data here. So you can play with different kind of data, and as you choose your data here, your data is also changing over here. So I'll just start with some simple data here. Next is your ratio of training to test data. Usually we train it on 70% of the data and test on remaining 30%. So I'm going to choose it to 70. Here's your batch size. If I go it all the way to 1, then I'm looking at the stochastic gradient descent, but I want to have it some form of a batch. So I'll get it up to 20. And here are the features. So we have x1 and x2, and there's just 2 features here, but you could also construct new features. So as a remote sensing scientist, if someone gives you, NIR band and red band, a natural instinct is to think about NDVI. So NDVI is another additional features that you could derive from your input data set. Similar in this case, you have x1, x2, you can choose, x1 square, x2 square, whatever you want. In this case, I'm just going to choose x1 times x2. And here are your hidden layers. In this case, there is 2 hidden layer. Should be suffice, but I'm just going to go and add one more hidden layer here. So I have 4 neurons in the first hidden layer. I have 3. I'm just going to add 1. So I'm dropping out one of those hidden layer. And then on the third, I have another dropped out one hidden layer. And now if you look at the top here, you have learning rate here. You can choose between this learning rate. I'm gonna go and choose 0.01, and then different activation function. I just want to keep it simple, so I'll go and choose ReLU in this case. And then there's some form of a regularization here. So we saw that dropout is one way to avoid overfitting. The other way is using regularization layer. So let's say you have a very large project, and you have like thousands of features that you have used in that project, and you're not sure whether all the features are important for your problem. In that case, you could use a L1 regularization, which is a Rees regularization that basically will determine which of those input features are important, and if it finds that some of those features are not really important, then it will assign its weight to 0, eventually dropping out that feature. But if you have a project where you know that all of these features are really important, and you just want to regulate it or provide some form of a penalty, then you could use L2 regularization, where it will take that feature, an let's say unused feature, to really close to 0, but not actually 0. So the feature is in the network, but it's not contributing as much as the other feature. For this case, I'm not going to use any of that. The regularization rate is again associated with the regularization. This is a classification problem. So let's go ahead and run this. So you see that while it's running, it's forming these boundary layers in here. So yeah, so let me stop here. So it has a near perfect classification here. And we saw that it ran up to 523 epoch. So one epoch is when the network sees all the data, because remember, we are providing data in a batch. We're not providing all at once. So it takes several steps to even even the network to see all the data. So one epoch is when the network has seen all the input data, so that it has to train up to like 523 epoch to get to correctly classify the problem that we have in hand. So next, I'm just going to go and change our learning rate here, and I'm going to restart the epoch. And when you see that, it just takes like 100 epoch to come up with that classification that we saw before. So again, the learning rate plays an important role here. It's determining like how much of the steps it should be taking. Cool. So it's really cool website put together by the TensorFlow team. So I'll highly recommend check it out. It will give you like tons of idea on how you should control some of these parameters. Okay, for today's hands-on, I have a notebook ready. So for today's hands-on, we'll be extracting our data from Google Earth Engine. Team showed us many of those pre-processing and data pre-processing steps yesterday. We'll leverage many of the data sets that's already prepared, and then within a Google Cloud or a TensorFlow environment, we'll train that model. Once we train that model, we'll then predict the output from the model, and then we'll upload those results back into the Earth Engine for our visualization purpose. So moving, before we start, I just want to say TensorFlow is an open source software library that supports many of the machine learning and deep learning algorithms. The TensorFlow relies heavily on Keras, which I'm pretty sure many of us have heard. And then we'll run that in a Colab notebook, which is basically a free Jupyter notebook environment that requires no setup, and it runs entirely on the cloud. Okay, awesome. Before we go to the hands-on, is there any question? And I'll link to the notebook here.
I just added it, Biplav.
Okay, thank you.
One note I'll make, actually two notes. When you open this Colab notebook, and Biplav will mention this too, just make sure you go to File and you can save a copy to your drive, because this is hosted as like a notebook that Biplav owns, and you can save a copy right to your Google Drive, which is really, really, I love Colab. It's really fantastic in that way. So that way you can run all the things on your side. And then one other thing I'd mention on Biplav's lecture is the optimizers and the dropout, and there was some discussion about like hypertuning. Like that's really into the core of like making a good model, right? You can just use a DNN and produce something, but then there's all these different components that you can put into the model architecture and design that really improves the efficiency, like Biplav mentioned with the AlexNet. So you can totally get lost in finding the best way to produce a product, and it's really exciting in that way. But don't feel overwhelmed, because there's so many resources that can sort of, based off the question that you have, you can actually come up with a pretty strict set of rules to sort of weed out some useless or lower value optimizers, things like that. And they also have like TensorBoard, things like that, which are really designed for hypertuning, that removes a lot of like, oh, I have to have all this domain expertise to know all these different optimizers, right? You don't necessarily need to know that. You just need to know your input data is a good place to start. So I just wanted to put that comment out there.
Yeah, thank you, Tim. Yeah, okay, let's actually start with this notebook. If you want, you can go and run it along with me, but I'll just go ahead and run it. You have the notebook, so you can run it on your time. As Tim mentioned, go ahead and save a copy in your drive. If you make any edit, it won't save on your end, because probably you only have a read-only permission. So if you want to retain a copy or make any changes on the network, then please go ahead and save it. And you could also see the output here when click this NB viewer. Yeah, so this also gives you basically the same output that you saw in this Colab notebook. So okay, let's go ahead. So in this notebook, I'll show you how you can export the training and testing data set from Google Earth Engine into a TF record format, a TensorFlow record format. So this is a format, you could, in TensorFlow, you could provide data in different kind of format. You could have a NumPy array, you could have different other Parquet format or whatnot. But for this one, we'll be looking at the TF record, since the Earth Engine can directly output those data in the TF record format. And then we'll see how we can prepare those data for use in a TensorFlow model. Especially we'll be looking at the deep neural net. So it's a very simple neural nets that I'm pretty sure after the concept that we explained, you should be able to understand what's going inside of it. And then we'll see how you can make a model in the TensorFlow. So as I mentioned that TensorFlow heavily relies on Keras to do some of its backend. We'll be looking at a sequential method to produce this model, and also a functional method. The difference is that sequential method is relatively easy, but if you want to go and make like a really complicated model, then you probably want to go and use a functional model in those cases. And then we'll see how we can make predictions on the image that we exported from Earth Engine, and how we can ingest those classified images back into the Earth Engine. We'll see three sort of ways you could inference. So we talked inference briefly yesterday. Inference is more like making predictions using your trained model on an unseen data. So we'll see a classical way where you can download an image image from Google Earth Engine, produce the output, and then push that output back to the Earth Engine. That's a very classical way of doing it. I'll also show you an AI platform, although I found that this hasn't been working that great. And if you are attending the Geo for Good this year, uh, this is again insider information. So a Vertex AI platform is where the Google wants to take the inference for integrating it with the Google Earth Engine. So I don't have any code example here, but this is something that you can, after Earth Engine Summit, you'll be able to do that. So I'm going here and importing Earth Engine and several other libraries that I would need in order to run the subsequent code base. So here I'm EE version of 0.1. We're using Folium to visualize. You saw that Earth Engine. So yesterday we saw a code editor version of Earth Engine, which is a JavaScript form. You had a place to write your code. Here you had a place to write your code, you had a place to visualize your result instantly, you could print all those things. So if you want to visualize something on a Python API, because today we'll be using a Python version of Google Earth Engine, you need a Folium. There's also other libraries like Kusanwu's Gmap is pretty famous, you could also use, but for the sake of simplicity, I'm just going to use Folium for now. Next, you need to define a cloud project. I think we need to have some discussion at the end on some of these resources. But for the sake of this project, most of the training data set that would be used should be already public, and you should have access to it. Okay, and then we're using this bucket within that cloud project. And here I'm just going and authenticating the Earth Engine, the Google Cloud, the Google Colab to run things on my behalf. Okay. Okay, so now we've been authenticated. So now here we'll define some of the variables that we'll be using. For this, we're focusing on 2019. Sorry, I forgot to mention. So we're looking at the illegal gold mining, the similar application that we saw yesterday using the random forest. For this, we're using 2019 as a coordinate for me to focus that map on a certain point. So it's a random spot on the study area. Is the study area coordinates basically, and the output, the scale. You need yesterday we used 70% for training, 30% for testing. Today we'll be using 60% for training, but then within the validation. So remember, when we back propagate, it's looking at those validation data set. So we'll be using 20% of that to adjust those weight, and then the remaining 20% will be used to classify an unseen data set. Number of classes in our case is 2, mining, non-mining. Here we'll be using 2 data set. We talked a lot about data set yesterday. Amil mentioned, sorry, Glory, go ahead.
I was going to raise the same points that Salim raised about the error that is we are not able to authenticate. But I think Tim is already addressing it.
Yeah, if you give me your email address, I can add you to a Google group, and that will give you access to the space to compute. So just if you run that error, just keep sending it my way.
Thank you, Tim. Yeah.
Mhm.
Amil mentioned about hyperspectral images and other several types of images. For this, we'll be using a Sentinel-1 and a Sentinel-2. For Sentinel-1, we're using VV-VH polarization, and we're also taking a ratio of those. We're also calculating an ND ratio. So this is very similar to how you calculate your NDVI. Your NDVI is NIR minus R divided by NIR plus R. So in this case, the Sentinel-1 ND ratio is VV minus VH divided by VV plus VH. So again, these are like the derived features, right? Because we only provided with VV and VH, but we're also deriving these. And then within Sentinel-2, I'm using almost all the bands that it's provided. I'll also produce some of the additional features like NDVI, NDWI, EVI later on the slide. Here's our output band. There's some mining band. I have this as an old label. We saw that the CID was what was representing a label in yesterday's case. We have that, and then these are some of the other prefix that some of the other variables that we need. And here is where we define the epoch. So again, epoch is where your network sees a full training data set. We want it to train up to 20 epoch. And then we're using a batch size of 32 in this case. So I'm gonna go ahead and run that. Next, so I have some helper function, and we'll see where those are useful in a bit. So these are the feature collection that we saw yesterday. I exported them as a feature collection, and you should be able to import them easily here. So here's some of the Galamsey point that we added and some of the non-Galamsey point. So I'm gonna go ahead and run it, and this is another training point that we already have within the services. So we're also using that point. So beside this Galamsey underscore PTS, the user added Galamsey and the user added non-Galamsey were the extra points that we added using Google Earth Engine. So when you run this, and I'm here aggregating based on this old level, which is a CID, and it's saying me that there are like 2000 points here, and the value of all of them is 0. But since you probably wanna flip that, because 0 would probably represent non-Galamsey and 1 would represent Galamsey. So here I'm applying a map function and calling this inner function within that map function, set class level. And so the set class level basically, we have output bands here, which is a mining. So it assigns a new label called as the mining and put it the value of 1. So when you run this, and when you again aggregate it over the histogram, you see all those 2000 points now have a label of 1 instead of 0. And now if you run the Galamsey point, I'm getting the first feature in that feature collection, printing out it information. Again, also doing the same thing for our user added Galamsey and user added non-Galamsey. When you run that, we see that there's still some of these CID, the old label, that exist. So in the next line of code, I'm just going and setting a proper name for our feature collection. So when you go and run that, you see now you have a mining, and mining. So we have a feature collection with a proper property name that we can easily now combine together. So that's what we are doing here. We're just merging all of that into one variable called as the all underscore points. And then on the next set of code, again, using Folium to initialize our map. My starting location is the random location within that study area, and then starting out at a zoom level of 8. And then I'm adding all these points. So in this case, I'm adding Galamsey points, including the already provided Galamsey point as well as the user added Galamsey point. I'm also adding non-Galamsey point, and then painting the outline of the study area, which is the regions in this case. So when you go and run this, you'd see a region which is this outline, and then you'd see non-Galamsey point as a red, a Galamsey point as green. So next we'll prepare our Sentinel-2 dataset. The Sentinel-2 dataset, there's also a cloud probability, that's a separate image collection provided. And then there is a harmonized dataset. So we're combining those two dataset based on the index, and then merging them together. That way it will now have, each of these scene will also have the cloud probability value associated with it. And here I am basically taking all the points, dividing those by a scaling factor of 10,000, and then taking only the images whose cloud cover are less than 50% in this case. So when you run this, you get this image now, which is a composite image, which is a median composite in this case, between your start and the end date. So next we'll just go ahead again here, similar to what we saw before, initializing the map, adding that particular image to the map and visualizing it. Okay, so now we have this composite map. Next, we'll generate our data to actually run the model. So in order to generate the data, what I'm doing here is I'm just assigning a random column. So it randomly put out a column name as column, and here's the seed value. So this is more of a stochastic nature. So when you also repeat this experiment, you'll also get the similar result. We talked a little bit about that yesterday. And then I'm selecting my training sample by basically those random columns whose value are greater than 0.5, so 60% of the data here. And then the validation data is still used while in the training phase, but it's something that is used to adjust the weight. So I'm taking that 20%, and then remaining is our test sample. So again, 20% of the overall data that would be used to make the prediction on an unseen data set, and that would really help us to understand how our model is performing. And then I'm just printing some of the sizes here. So if you go and run, this is the first feature. It has a mining and then a random. And then here's the sample size. We have around 3,200 points, training sample size, validation and test sample size. And then we're also printing this distribution to see, to make sure that validation sample also has mining and non-mining points, or whatever that is. So it also provides you this distribution. So now if you run and go and run this again, and doing a similar thing, initializing our map, taking our training sample, validation sample, test sample, putting them in a map. You can see the result here. So here's our training point. Our validation point is this red one, and then the test point. Okay, so now we have all our training data and everything here. So next we need, because this is an image collection, we need to find a way to convert that to image. Sorry, it's a feature collection. We need to find a way to convert that to an image. So here I'm just taking an empty image and then painting those points with the values coming from the mining column in our feature collection. And then our final image has the Sentinel-2, which was the previous one, and then added this label image here. So if you go and run this, it's run without any error. So one of the caveat using Earth Engine is sometimes it can run into this computational timeout error, especially if you have a massive computation that's going on. And that's sort of the case with us, especially when using the Sentinel-2 dataset, because you're using two image collection, but then you're also joining them. So it's a very computationally heavy process, and if you try to just sample from this image, you'll run into the computational timeout problem. So to tackle or to get around that, we're gonna go and export that image. So if you are actually exporting it, change that to true. For this purpose, I've already exported the image and you should have access to it. Oops. So yeah, I'm not gonna export it again, but the assets should already be there. And this is basically, if you had exported it, it will wait until that task is complete. Okay, so now we have the Sentinel-2 data, and I exported that as s2_2019_ remember, this also has the label in it. Then we also have this Sentinel-1 data, and I went ahead and run the same script that team showed us yesterday for that study area, and I have it exported and provided here. Next, I'm going and selecting those bands within that Sentinel-1 composite and renaming that to our s1_bands, which is, in this case, VVVH, and then just appending this S1 underscore ratio and S1 underscore ND ratio. Okay, so that's what's going on here. And then here's our final image that has our Sentinel-1, Sentinel-2, as well as our label in it. And next, just printing the band name. So here we have all our input and the output bands correctly in that image. In this function, it's just sampling an image based on that feature collection on some certain scale. Yeah, here is where that function is actually called using our image data. That's the final data that we produced above. And then using our training sample location, validation sample location, and test sample location, we are producing training, validation, and test point. Just doing a sanity check to make sure everything is correct before exporting it. So when you sample it, you see all these values that sample from that particular points. So it looks like we have everything correctly in order. And in this line of code, because we need to export that to cloud storage, I'm setting up a function to do that. Here's the name of the output files that we want.
Hey, Biplav, can you just stop sharing and then reshare? A couple people saying that they cannot see.
Oh, okay. Sorry about that.
I can see it on my end, but it might just be a network thing.
Okay. Can you see now?
I can see it. I was seeing it also.
Okay.
Yep.
Thank you. Okay, so now we have our training data set, validation data set, everything, right? So again, I'm not gonna start this training because I've already exported that. But if you want to do that, just change that to true, and you should be able to, export that. So once you just want to show how it looks like here. So once that training is successful, you would get these TF record data point. So I have illegal underscore mining underscore testing. That was the name that we provided. Testing, training, and the validation data set. So this is inside the Google bucket WA underscore TF underscore training. If you go up where we were declaring variables, this was the name of the bucket we put, and then the name of this project was Servier-EE, the cloud project that we put in there. So now we have our training data, testing and validation data. Again, this is going and checking those tags until it's finished. And here we're just going and checking whether those data are available in our cloud bucket. So the way you access the cloud bucket is using this GS colon // the name of the bucket, which in this case was WA-TF-training, and then your training, the name of your training file, which we declared is as illegal underscore mining underscore training, and then this is the the suffix of that file name. So gonna go ahead and check using the TensorFlow function to see whether those files exist, and it says it exists. And we also confirm that by looking at our cloud at our bucket as well. So in this couple of line of code, we are setting up so that the TensorFlow understand what kind of features or what kind of columns that we are gonna give to the model. So we saw that here we saw that the value is just a scalar, or a simple 1D vector kind of thing here. If you put it inside a array, it would be a 1D vector. So but if you are using, for example, let's say convolutional neural network, then you'd have a different dimension. You'll probably have a 2D dimension, but in this case it's a 1D. And then we're saying that each of these would be a floating point value. Let's go ahead and do that. Now you have if you go ahead and run this, you have this dictionary where your key are the bands, and then your values are, something that TensorFlow can understand, which has a shape, 1D shape, and a data type of floating 32 point. Okay, so this is a helper function. We'll see that where it's useful. In the next line of code, we're just reading those files, and then we are creating a TensorFlow record from those files. And you do that just simply by calling this tf.data.tf record data set and providing the name of that file. So I'm going to go ahead and run that. Okay, that ran successfully. Next, now the network knows like what kind of data to expect. It hasn't actually seen the data itself. So these set of helper functions would help us to feed those data into that dictionary that we saw before. So this particular function is just parsing our TF record. Again, we saw that before. And then in this one, oops, sorry. I was looking at the wrong function. So once we created the data, we need to parse that. So you parse that by using this parse single example, because each of these each of those tensor have a single example in it, and you're parsing it and you're providing the dictionary. So these dictionary, so it will go and match these keys with the data itself, and it will parse it in a way that's understandable. So it will treat everything as a floating 32 point with a shape of 1. In any of this case, for example, you exported a 2D data, you exported a convolutional data, and you provided it a shape of 1, and then it's gonna throw back an error saying that the data that you provided and the abstraction that you said are different, and I don't know what to do about that. But in this case, that's not the case. We successfully parsed the features. And remember, that feature also has the label in it. So we want to take the label out from that. The way TensorFlow accepts the data to train is it needs a tuple of data. The first element on that tuple is the feature, and the second element on that tuple is a label. So that's why we are extracting that label out from the parsed feature. And here you can see that we are actually converting it to an int 32 because it's either 0 or 1. So that's what's going on. And here again, transposing it. So if you have an array of array, you want to put that in a single array kind of thing. So it's basically doing that here. And then here we are applying a one-hot encoding. So one-hot encoding is, for example, let's say you have two classes, and same what we're dealing with here, 0 and 1. And let's say you have one example which has a label of 0, and there's another example which has a label of 2. Level of 1. So what one-hot encoding does is that for this first label, it will convert that as 1 0, and then for second level it will convert that as 0 1. So it's a way to provide a label. And let's say you had 3 classes, then 0 1 and 2, then for this one it would be another 0 appended at the end. And let's say you had another example with a value of 2, and then it would have been 0 0 1. So you get the point what one-hot encoding is doing here. Yeah, we're just using that function to parse them. We are first parsing our training data. I'm just going to go ahead and parse it. So now we we had the abstraction provided as a feature dictionary, and we also pass our actual data in it. So let's go ahead and look at one of the example point from our training data set. So if you run this, again, you're getting the same thing, but now you actually have the actual value that the network needs. Okay, so we have data ready to go in. But before that, we also are interested in creating some of the additional features, because we are remote sensing scientists and we have so many bands to take advantage of. So here, we're just, again, doing the same thing, adding NDVI, EVI, MNDWI, all these things. So if you go and run that, next, once we parsed our data sets, now we're gonna add, extra features into our data. So we have 5 extra features that we have added here. And then on this line of code, so once you have your original data as well as the feature added feature data in your data set, you need to shuffle. So you need shuffle again to avoid those sequential dependencies that the network might encounter. So you're just shuffling your data, now batching it into some batch. And then prefetch is something where, if you have when a model is running, the model usually runs your data. If you have GPU, the model will normally run your data on the GPU. I mean, train the data on GPU. But on the CPU, you can use that time to prefetch the next example ready for the model, so it doesn't lose any time in between. So that's what we're doing here, and we're repeating the same thing here. Same thing with our validate data set. Next, we're gonna set up our model. I mentioned that we'll be looking at 2 major way. This is the sequential model. So the way you initialize it is tf.keras.models.sequential, and then you have all these dense networks. So remember those neurons on your head, and then how many neurons? 128 neurons. And what are the activation function that you want to use in each of these neurons? You want to use the railway activation function. Again, go ahead and play with different neurons and different activation function. And there are, in fact, other options that I haven't used with this function, so you can also go and check that out. Yeah. And then again, dropout, don't wanna overfit it, dropping out at after the dense layer. Again, doing the same thing but decreasing our number of the neurons. Again, dropping out, decreasing our number of neurons, dropping out, and then this is the last layer. So we talked about like activation function before, and in this case I'm using a sigmoid activation. So sigmoid activation, as I mentioned before, produce an output between 0 and 1, where the sum of those values equals to 1. So you can take that as a probability. That's what's going on here. And we need the final output because we have only 2 classes. We'll only have the final output as a 2 class. So we have defined our model here. I've given it a name model 1 because we'll also look at functional way, which we'll call it model 2. And then we're gonna compile that model. So we know the internal structure of the model, but we also need this optimizer, what's the loss function, and what's the metrics that we'll keep track of. So go ahead and run that. So you have a model that's compiled. Next, the way you now actually feed in your data to that model is by using this fit function. And your X in this case is a trained data set, number of epoch, and then this is like how many steps needed to be taken to complete an epoch. That would be your number of training size divided by your batch size, because you're providing that many batch of data at one go. And then using the validation data set to see how the model is performing and adjust those weights and biases in the network. So when you run this, yeah, it's running for an epoch of 20. It's a very simple network, and it doesn't has like tons of data in it. It's just 3000 data, so it runs relatively faster. But trust me, if you have like millions of data, this could take a while to run this. Now here you can see our loss going down as it should be, accuracy going up, it should be, and these are on our training data set. And here is our result on the validation data set, validation loss. Again, it looks like it's doing what it's supposed to be. It's the accuracy is, it's fluctuating, but it's on the higher end. The validation loss is also decreasing as we are training the model. Next, we can run this dot summary method on that model, and it will tell you how your model actually looks like. So we had like first dense layer, and this is sort of the input saved that's been provided. So we had like 128 neuron. Remember, this was a 1D data set. And then this none is like batch of data. You could have as many batch of data as you want. So none simply signifies that it can accept as many batch of data as it can. And then dropping out another dense layer with 64 neuron, dropping out another layer with 32 neurons, dropping out, and then our final neuron with the desired number of class. So here's like there's around 13,000 parameters that this model is training. So next we'll see similar example, but in a functional kind of case. So the functional APIs in Keras is normally used in this way. The line number 18 here, you have keras.model.models, and you provide what's the input and what's the output to that particular model. So if we now go back and look, our input is again specifying this shape. So shape of none, and remember we had in the beginning we had like length of input shapes, but then we also added those 5 extra features which I'm adding here. This is sort of the input layer, and then I'm doing here something extra. It's doing a convolutional, but in a 1D convolutional. I don't want to go into detail in this, but it's just another way you could also construct a DNN model. And then once these convolutional max pooling are carried out, here what I'm doing is I'm taking this original input data set and then also adding it to this convolutional that it ran, and then basically doing the same thing that we saw before. So if you run this and also run this model.summary, you'll see what's going on in this. And then now let's go ahead and actually train the model. So this one is a bit complex model than the one that we saw before. It has like 51,000 parameters, and this one has 13,000 parameters. You might think that the more parameters you have, the better the model is, and that's not always the case. And we'll actually see that hopefully here. Again, keeping an eye on loss decreasing, accuracy is increasing. Similar is the case with our validation loss and the validation accuracy. Okay, so now our model has run. So next, we have two model 1 and model 2. We're gonna test the accuracy of those model in an test data set. So we hadn't used test data set for our training purpose. So we'll use that in order to evaluate the model. Again, doing the same thing with our test data set, adding all these extra features in it. And then now let's evaluate our model 1 as well as model 2. Yeah, so we saw that model 1, which was pretty simple model, has almost same accuracy as the model 2, which was a bit complex model. So you just have to play with different model architecture. it's not always the case that the complex model you have, the better answer you'll get. So now we have model, we have evaluated, and we're happy with what we're seeing here. So next step is how we're going to use that model to actually do the prediction or the inference. And there's 3 ways you can do that. The first is where you export the data from Google Earth Engine and then make predictions on those data and then push it back to the Google Earth Engine. That's what we're doing here. But before I do that, we need to extract those images from the Google Earth Engine into a TF record format, because that's sort of the format that that our model natively understands. So I'm doing that over here. And I'm taking a very small area in this case because this takes quite a bit time to actually complete the inference and everything. So for the sake of example, it's a small area. Again, I already have exported that image, so I'm not going to go and export again, setting that to false. Again, checking that export tags here. Okay, so now once that export is finished, if you go and look at your Google Cloud bucket, you'll see that you get all these images. So this was the images that we exported. It divides it into, because here we specify like the maximum file size, and we want it in a compressed format. So here it's dividing those data into different file size. And then there is something called as the image mixture.json, and image mixture.json has information on like what's the affine transformation, or how many patches are there, what's the tie points, or what's the coordinate that needs to be tied. All those things, all those informations are provided in this image mixer data set. So okay, so here again we're doing the same. We're going and getting our list of images, and we're also getting that JSON mixture file. So if you run this, now you have all these images and then also this JSON mixer file. Next, we're just reading that JSON mixer file. As I mentioned, it has all this information on georeferencing, a number of patches. So we'll use that information here. So in this particular line, in this block of code, we're again doing a similar thing. We are getting our image data set. We're constructing, what are the bands in that data set. Remember here, we haven't taken our output band because we are now predicting on an unseen image. And then we're adding all these NDVI, EVI, MNDWI that we needed. Yeah, so when you run that, because now we have our image data sets that's ready to be used for the prediction purpose. We're using .predict method on that image to get our prediction. And again, I'm not gonna run this because it takes a long time to run. But at the end, and here I'm printing the prediction like how it looks like. It gives you this array of array, a list of list, where your first number determines the probability associated with your 0 class, and your second number determines the probability associated with your mining class or 1 class. Again, printing that similar thing. Now we have all these predictions, right? Which has, if you look here, it has like almost 1 million, more than million of pixels in it. So when you run this, it's again gonna take a long time. But basically what we are doing here is we are constructing 3 bands for our image. The first band is our prediction band. The second is non-mining probability band. The third is the mining probability band. So the prediction band is basically taking the argmax. So argmax in this case would be it's taking which one is maximum on those values. So the maximum in this case is 0.8, which is 0 level in our case. So this argmax basically does that. It gets the maximum, the highest probability, and assigns that particular prediction class. But we're also taking the actual values coming out and putting them in this non-mining probability and the mining probability here. So when you run this, you see here, it has like 208 patches of data of 256 by 256 patch dimension. So it will go and run that until it completes all those 208 patches. Now we have the data. We uploaded that data to our WA_classified TF record. So if you go and look the data here, we have the prediction here, right? WA_classified.tf record. Again, this prediction, remember, only has numbers in it. It doesn't know the geographical extent or where that lies in the earth. So in order to do that, we'll use this upload image function. We'll provide it with the output asset file, which is this classified image, and then we'll also provide it with a JSON file that will that looks at the JSON, and it understands what are the affine parameters that needs to be applied for that image to georeference it. So when you run that, it will start uploading that image to Earth Engine. Once your upload is complete, then you can go and visualize that result. Oops. Need to define this variable here. So again, here we are taking prediction. Remember, that was our band name. We're taking mining probability, we're taking non-mining probability, and then visualizing it in our map. So here's the result. Let's look at the prediction. So here's our prediction. So the white is where the model thinks is the mining happening. The black is where it doesn't think. Then here are the probability. This is the mining probability. So the brighter color, the more white color, the higher probability. The more black, the lower probability. Similar is the case here, non-mining probability. Awesome. So this is sort of one way of inferencing. The next way is using the AI platform. Again, this hasn't been working when I last checked, and I reached out to the Earth Engine team, but they haven't got back to me. But basically here we are uploading whatever our model is. So this is the model 1 dot, and then we are saving that to our bucket. Once we save our model to the bucket, you have this folder here, and when you go and look at that, and this is like sort of all the model in a format that can be consumed by the AI platform. Next, we are preparing our model to be exported to Earth Engine. So you basically run this, you provide the model directory, and then where you want to save this model, what are the input and the output. And next, once you have this EE5 directory, you can use that to host your model in an AI platform, which is sort of what's going on here. Yeah, next, once you have your model hosted, so if you go and look at the AI platform, and then go and look at these models, this is the model WA_TF_ model. So this is the model that's on our AI platform that we'll be using to make the inference on the Google Earth Engine side. And the way we do that is by using ee.model.from_API platform predictor, and there are like several parameters that you can specify, which I've discussed extensively. And then the third is again using the Vertex AI platform, which will probably have after October released publicly. Okay, that's all I have. I know I went a bit longer, but I hope that was helpful.
Thanks a lot.
Take any questions, and maybe we can have some discussions. Oh, is everyone ready to play games? Okay, let's do that. Okay. Awesome. So pin is
I'm going to play. I haven't seen any of these questions, so I might get totally smoked here and be really bad. But
nice. I actually made these questions this morning, so I haven't used Kahoot before, but it looks pretty simple. So
and remember the answers will be on the screen, or the questions, the options will be on the screen, and it'll only be like a color or a symbol, color and symbol on your device. So like green, diamond, I think is maybe the correlation there. But Bipov will just read the questions as they come.
Yeah. So we have around 31. Oops. Okay. It says the player limit reached. Okay. We can start. So I'll go ahead and get started with our first question, which is one. Okay, it's a true false. So the first question is deep learning was first introduced in 2010 after the advent of large dataset and powerful GPUs. We got 5 seconds. Awesome. That's false because the concept of deep learning was already introduced back in 1950s, 60s, but it really bloomed after 2010. So going to the next question. Oh, Mary, we have Mary on first, Jacob is second, Aluko, Emil, and Tim. Awesome. Let's move on to our next question, which is a quiz. So what does the loss function in machine learning measure? Remember, we talked a lot. The machine learning, it measures the learning rate, the accuracy, the error or difference between the prediction and the true value, and the number of layers in neural network. Yes, the loss function, we talked about mean square loss, mean absolute loss. binary loss. So this actually measures the output from your prediction and the true value, so it can adjust those weight in the back propagation step. Okay, let's see the scoreboard. Team rising to the top. We have Cobbs on second, Nick on third, Dennis and Mary. Okay, so let's go to the next question. Again, a quiz. In which phase of the neural network training is the error computed using a loss function? So is it during initialization phase, or forward propagation, forward pass, backward propagation, backward pass, or it is during the optimization step? Nice. Oh, only two. Okay, so maybe I didn't explain this correctly. So once the training data is passed through the network until the output layer, so at the very end, at the output layer, once the model predict what's the output is, it will look at the level data and it compute the loss during that time. So it's everything is happening on that forward pass. Okay, let's see the scoreboard. Team still at the top. No change in leaderboard. Okay, let's move on to our fourth question. So a binary classification task, that's the one that we use today. What loss function would be most suitable? Is it mean square loss, binary cross entropy? Is it Hoover loss, or is it a KL divergence loss? Last 5 seconds here. It is the binary cross entropy. Most of us got that right. Oh, Mary climbing. Glory is also climbing. Okay, let's go to our fifth question. What type of gradient descent computes the gradient using an entire data set? Is it a stochastic gradient descent, mini batch, batch gradient descent, or momentum based gradient descent? Remember, we talked you can pass all data at once, you can pass one data at once, but you can also pass batches of data. Sorry, mini batches of data. It is batch gradient descent. You're just passing everything in one batch, one go. Ooh, Dennis climbing. Jacob is picking up. Team, you're fourth now. Cobbs is second. We have 3 more questions. So this is our sixth. Which real-world application uses reinforcement learning to navigate street? I think I just gave up the answer there. Is it chatbots, recommendation system, self-driving cars, or image classification? Last 5 seconds. Yes, it is the self-driving car. We talked a lot about like how the agent is involved, then you give it some environment, it will do some action. Based on that action, you will either give it a positive reward or a negative reward, kind of like how you train a dog, you know. So yeah, most of us got that right. Cobbs climbing up, Dennis at the second, Mary still at third. Aluko is the highest climber. I don't know what the climber is, but okay. Second last question. This is a quiz also. So what does back propagation use to compute the gradient of the loss function with the model's parameter? You remember something happens before doing the back propagation? We compute the gradient. So how do we compute that gradient? Do we use integration? Do we use differentiation? Do we use multiplication? Or do we do division? Yes, so we use differentiation. We talked about, you know, the chain rule of differentiation. Linear algebra is all that's applied when the back propagation is going. Mary at the top. I like these changes in the scoreboard. Nice. So this is our very last question. So again, true, false. During the backprop, gradient are calculated to understand how much each parameters contribute to the error. Is it true or false? Last 10 seconds. Probably it's very easy. Yes. So during the back propagation, remember we use the gradient descent algorithm to calculate those gradient loss, so we could adjust the parameters. Okay, let's see the final score. And our third place is Denise. Second place, Nick. And at the top is Mary. Congratulations. Runner-ups are Tim and Jacob. Nice. Oh, that was fun. Yeah, nice job. Okay, sorry I took most of the time, but maybe we'll have some discussions, and if you have any questions, please. And we'll also talk about some of the next steps in after we have some discussions here.
Now, if I shoot first.
Yes.
Now, Tim, the first thing that comes to my mind is this buckets. It's clear that unless we are added to a group, we won't get access to that. And that also means that any one of us right now, even in this meeting, that have not sent in his or her email will not have access to running this, repeating this exercise in Colab, which means we cannot really repeat this exercise ever, as it were, except we, of course, we contact you. So is there any way we can go around this?
Gloria, I was just going to add a comment here at the very beginning. Each person with an email account can sign up for $300 of free credits. So if you go to google.console.com, I think, you can sign up and create your own bucket individually without an institution or anything like that. And $300 will get you really far. It's for a full year. So if you want to, you can just explore this type of workflow with free credits. So that's a very initial step. Like when we did the TensorFlow working group or the TensorFlow exchange back in 2019, we were able to run the whole workshop with those $300 individually, and you can go a long ways with that.
Sure.
The second point there is to do this type of to leverage this algorithm, it's going to cost. It's way more computationally intensive than something like random forest. And then there should be a lot of upsides to that, right? If you're going to pay more for it and you're going to do all this work, hopefully it's going to squeeze out more value in your prediction. But just know that is and always has been sort of a challenge of leveraging this system. There's a lot more startup energy that you need to do, both from a financial standpoint and a knowledge standpoint, to get to that place. Those are some negatives. And then the last thing I'll mention here is, we are, as a field, all sort of moving into cloud computing, right? That's just going to be the wave of the future. So I think taking these sort of intermediate steps to start using this type of technology is really important. And we're here definitely at SCO to help folks at West Africa explore that. We've got a lot of other science tools that leverage cloud. We just only use Google Cloud Platform today, but there's other resources that we can talk about that are from the private industry as well as NASA resources that we have access to. So more about like sparking your interest, and then we can explore sort of the resources we have, and also West Africa has, and in addition to that, Socrates. So there's a lot of different solutions. It's all about sort of leading in that direction. And Biplav, over to you. I know we talked about this as one of the main discussion topics.
Yeah, yeah, yeah. As Tim mentioned, this has been a challenge for us also here at SEO. I think the best way to get start is use that $300 credit. Just a side tip, you can, if you have multiple Google accounts, you can sign up differently, so you have more credit to you. Yeah, but that's something I think we will have that discussion at the organizational level. At least I hope before Geo for Good, and we'll have something during that time. But for now, the best way to use is just use just use the free credit for now. Yeah.
And we have a couple resources, like I mentioned, through NASA that are exploring, access to cloud resources for applied science. And we know that one of the major challenges, especially even with GCP, is from an institution to institution, how do we collaborate? How do we share costs? All those sort of like really complicated project management sort of questions. But we're also sort of exploring places that are sort of a neutral space that we can bring data, do some analysis, get some outputs. So those are a lot of internal conversations we're having here. But I think for the day-to-day work, if this is really valuable and you guys are wanting to leverage this as like a pipeline for services, ultimately, I think we'll find a solution. Like I'm not concerned, because we've got, folks in like the Amazonia hub who are using this as an operational service right now. So the pathway has been blazed already. So.
Okay, there's another question on the chat by Mary. Can you talk to that?
Yeah, so Mary asks, since the concept of neural networks is based on the human brain network, is there a way to use the human brain system to break down the explanations for beginners so they get the concept easily? Yes, definitely. So yeah, you can think of neural network like a virtual brain. Just as your brain has these interconnected neurons that communicate to process the information, a neural network works in a similar way. So it has these artificial neurons that are connected by the pathways. So when you train a neural network, you are teaching it to recognize those patterns, much like how your brain learns to recognize faces or objects. Just like your brain's neuron can activate based on an input, the neurons on the neural network can also activate, fire based on the data they receive. So a neural network is like a simplified model of the brain that can learn and make decisions. If that's like an easier way to understand, you can easily compare how the human brain works.
Okay, thank you so much, Becca. I'm not so sure about Janet's comment. Janet, if you could just explain this. I am using Collab Pro and my positions are now halfway. What does that mean, please?
Nice. So Collab Pro, sorry, Janet. Collab Pro is because Collab environment only gives you certain computational resource for free, and it's not guaranteed. Like Collab has GPU in it. Let me just share the screen and show it what I'm talking about. So if you go to this runtime here and then go to the change runtime, you see that there are also hardware accelerator option. You can use GPUs, CPUs, and whatnot. But because this is a free version of Collab, if there is a resource conjunction, then you might not always end up getting a GPU. You might be assigned to a CPU. But with Collab Notebook, you're always guaranteed that you'll have some form of GPUs associated with it. Plus, you'd also get a longer computational time. So you can, much like Google Earth Engine, where you can start your tasks and you can close your laptop go do your things. With Colab Pro, you could do the same. So you could run a task, let it run, close your notebook, come back after 24 hours and see the results. So but you have to pay for it. And I am not sure like if every countries in the world has access to the Colab Pro. So that's another thing. But if you have access to it, maybe that's something you can try. It's a monthly subscription, so you can try for a month and see whether it's even useful to you. And Janet here has been using Colab Pro. Maybe you can share your experience a little bit on using Colab Pro, Janet.
Okay. All right. Thank you so much. I don't know if there are other questions, but I want to ask for, I don't know, I should say a favor. I believe this is like I said yesterday, the idea for this whole training was so that we could use this as a launch pad to think of how in West Africa we can meet more regularly and be able to learn together as a group, while we also join the TensorFlow group, the global. So what I want to request is it possible that somewhere along the line, sometime maybe later in the year or sometime next year, we invite you to again, and of course, the entire team over there in SEO, and say, come and talk to us about X, Y, whatever. Will you guys be available to help us with something like this? Because really, I believe that many of us are really willing and eager to move from where we are now forward. So that's my request.
Yeah, Gloria, that's
trying to get a commitment here.
That's great. Yeah. And I think we also talked with Sabiri on this front too. You know, I think we're really positioning our time here at SEO to be as valuable as possible to the hubs. And we know that you guys are really interested in this. So we have found, I'm just going to talk the history of the TensorFlow working group. After we had this exchange on sort of data science and machine learning and deep learning, we were there for a week after the Geo for Good event with some folks from Google. And then we realized we actually found out all the things we don't know. Like, it was kind of humbling. We're like, oh, okay. We need to like meet every couple weeks and like spend time in this sector. And that was like 4 years ago. So if you're interested, this mechanism exists, and definitely come to this. But the success that I think we got early on is we defined some questions that we had. We wanted to identify where are some research areas that we should spend some time, like literally take an example and build a service around it. And that's where the illegal gold mining came up as a really great starting point. And Abena and Modu, who were there, we had an opportunity to kind of work with them for a few years. And all that knowledge also sort of translated to Amazonia as well, which is really great. Like, hubs were talking to each other in that way. So it really grew from identifying what the challenge is, and then using this group to get together and sort of answer those questions. So you're only really stumbling, you're working, and then you have about 2 weeks, and then you can come back and ask more questions and ask more questions. And it just helps to move along in a really fast and efficient manner. So I would say that we're more than happy to come back and talk and like give more overviews on sort of the field and different approaches. But I think for best results, like as a working group, as your guys' internal group here, I know that's what you guys want to identify as, like, get everyone in the room and grow skills. Identify 1 or 2 applications, and then we just start tackling them, and make sure that they're in the work plan and all the things that are necessary for the time and the value and the output of the product. You know, all that has to be solidified. But from the technical standpoint, I think we've got a good track record of these past years of like accelerating development and also building skills simultaneous. So yes, and
Thank you.
Feel free to add thoughts too.
Yes, thank you. That was very good. Yes, Bob.
Yes, and I think Mary and Mansoor are aware of this, but they're also gonna present at our working group on September 20, I believe. Yes, September 20. So on September 6, Amazonia Hub and Southeast Asia hubs are presenting. You could also attend those. Southeast Asia hub is really forward in using some of this technology, and they have even adopted that in various of their services. But on 20th, we want HKH team and South West Africa team to come and present on some of the problems that they want to work on during our data science exchange. Because it's a larger group, and there might be newer ideas, newer concept, newer workflows that we are not aware of and that the community aware of. So yeah, it's a great place to come and share your ideas and seek advice or suggestions. So yeah.
Yes.
Yeah, so we basically got 4 weeks or 4 opportunities in this TensorFlow working group between now and the Geo for Good event to really sort of ramp into what we want to talk at that data science exchange. And I know Mary and Mansoor, we've been talking about like sort of starting to refine a question that's going to be part of this exchange. So this could be a great vehicle, right, to sort of identify what's really valuable, and then solidify a team around it as well. And we're here, and all the other hubs, all the other hubs who participate, they're really interested in sharing their methodologies and growing together.
Okay, great. Thank you.
Yeah. Sorry, just to add, like if you see anything during that presentation from other teams that you are interested in, then we could also help you connect and get those.
That would be fine.
source
Great.
code as well.
All right. Okay, thanks so much. I think Mansoor is there. Go ahead.
And really, we need to have the record, because for the internet issue, the internet cut and we don't get all. But with the record that we can follow again,
Yes.
the webinar, and to understand some part.
I'll send those recordings to Jacob, and he'll share those with the group.
Yeah. Okay. Thank you so much. Okay, this is a good time, I believe, to end this. I want to thank you two so very much. I also want to thank Jacob and Emil. Super helpful, super support from behind. And then every one of us that have joined. Please, before we go, if you have not submitted any of the forms, kindly do so. I mean, this is important to me and to SEO as well. Just for the records, it's important that we do fill the forms. And like I said, please let us be ready. I'm going to send out a call. We have now been told it will be a good thing if we can really build this around one of our services. Let's start from a service, and then if we are comfortable, we can then move on to another service and maybe another one. So I will send out a call. I will expect that many of us will respond so that we can take this. Maybe we will decide when and how often we will meet. It will not be a single, it won't be my decision. It's going to be a meeting. We'll meet, and then we all decide how often we should meet, and also decide what we should need to do going forward. So I want to thank you all for being part of this. This has been very interesting, and I look forward to many more engagements like this. Thank you again, team and the other team. Thank you. Thank you very much.
Thanks. Thank you so much for your assistance in the training, and thank you everyone for attending. If you have any questions while you run Notebook or any of the code editor scripts, just reach out to us. We'll be more than happy to help.
Yeah, thanks.
Thank you all.
Thank you, everyone. Have a good evening.
And so